All right, let's go ahead and get started. Class 2. Today we will be talking about estimating a population mean, building on the material that we talked about in Class 1. Before I start, I just want to mention if you have any questions on any logistics, any Blackboard problems, any quiz concerns, any questions about how to do the Excel assignments, let me know. You can ask me now, or you can ask me at the break or after class. I know sometimes it's a little overwhelming getting all those working parts moving appropriately, and I don't want to overwhelm anyone with those kind of logistics, at least at first. We'll overwhelm you with the material later in the course as we go, but I just want to make sure you're feeling comfortable on that, and if you have any questions, please ask. So, with that out of the way, we can get to our purpose today of estimating a population mean. So, what is the average income in this town? Alright, that's a number. We want to figure out what it is. Can we ask every single person? Probably not. Can we take a sample? And can we develop some analysis around that sample? That's probably a little more realistic. So we're going to talk about sampling, how we would do that. We'll review the normal distribution, and we'll determine what that tells us about interpreting our sample. And that shows us this really cool thing called the sampling distribution of the sample mean, which will be the focus of our class tonight. That will allow us to develop confidence intervals. All right, we are 95% confident that the income is between 74,000 and 79,000, an interval like that. And then lastly, we'll do some real-world assumptions. Essentially, we'll take some baby steps, we'll assume we know things, and we'll say in the real world we don't know those things, what do we do then? So, with that, estimating a population mean, I mentioned already the example, what is the average income in this town? How much money do teenagers spend on video games? All right, that's an amount. All right, annually they spend this much money, or weekly they spend this much money. If it's a certain amount, we might want to try advertising, we might want to start building new products. If it's less than that, we might want to close our business. So we might need to find that out for an important business reason. Think about how we would. What is the average error rate in my production process? Another example of a population mean. What is the average number of times the coin comes up heads? Remember that experiment we did? We flipped a coin 20 times. What's the average number of times it came up heads? Well, there was a mean that we determined graphically. So we'll go through a thought process assuming we do not know that. And how would we sample for it? All right. So let's talk about sampling. When we sample, let me actually skip ahead to the crux of sampling. When we sample, statisticians use this term statistical inference. I don't want you to get confused by that. That's just a term that means we infer things. Infer. So if we're looking at an entire population, everyone in the town, we'll take a sample, a subset of the town. We will crunch some numbers around that sample, and then we will infer things about the whole population. All right, so that's all statistical inference means. Don't be intimidated by that when you see that in your textbook. We're just inferring based on our sample results what we think the characteristics of the whole population are. So, how do we sample? Well, let me give you an example or a question. Let me pose this question. Suppose we want to find the average income in the town. Do you think we would stand at a bus stop and ask the first 50 people we see, how much money do you make? No. Why would we not do that?
Because you're not going to get a good inference of the overall population.
Good, great job using the terminology. We're not going to be able to infer anything about the whole population. It's just a subset of people who uses the bus. Maybe people who use the bus don't have enough money to afford a car. That's why they're using the bus. We're going to get a biased sample. Similarly, we don't want to stand at the golf club and ask all those people how much money they make. Instead, we want a completely randomized process for our sampling, and we want an equal probability of every single person in town to be in our sample. We want it completely random, and we want an equal probability that every single person will be in our sample. That will give us a good, unbiased sample. Now, that's simple random sampling. Alright, definition, simple random sampling, a method in which ensures every combination of n members of the population has an equal chance of being selected. So, when we do these statistical tests, we'll just say we're assuming a good, simple, random sample. Now, to the question of why we might not want to ask every single person in town, or why that wouldn't be feasible, I think actually I skipped over that part, but let me go back a minute. Well, we may not have the resources to ask every single person in town. We may not even get reliable information if we try to ask every single person in town. We may have to hire a bunch of people to help us with this. They just may be college students trying to make a little money who don't really care about our statistical sample, and so they don't ask the questions the right way. They may try to take shortcuts. It's hard to monitor if we're trying to base results on every single person in this town of, say, 1 million people. And it is actually often better if we can take a good, simple random sample that ensures everyone has an equal probability of being in this sample, and we can have a small number of statisticians asking these questions, or not statisticians asking these questions, workers asking these questions and doing it in an unbiased way, and a way that doesn't influence the results of the sample. So, sample when we can, saves time, saves effort, and can be more precise. When we do it, we want a simple random sampling technique. And lastly, we'll be able to use information from that sample to infer things about the whole population. Alright, so let me do some quick normal distribution review. And where we're going to go with this is we'll think about if we have a sample, how does the normal distribution help us interpret that sample? So, in terms of review, remember we talked about the normal distribution last time. We mentioned the idea, the phenomena, that many things in the natural world will fall into a normal distribution. If I have a forest full of 20,000 trees, I'm going to have an average height of those trees. That would be the mean of my population. And I'm going to have a distribution of those trees. Some of those trees are going to be a little bit taller, some of those trees are going to be a little bit shorter, and the distribution measures how much, on average, each of those trees differ from the average height of the tree. Now, if there's an equal probability that one tree is going to be a little bit taller, to a similarly equal probability that one tree is going to be a little bit shorter, if those things are based just on random chance, then it will fall into a nice symmetrical normal distribution like this. And we said, suppose I'm talking on the phone with a guy in China who has another forest full of trees of 20,000, and he measures their heights and puts them on a frequency distribution. And we'd be on the phone and he'd be like, oh my god, that's so weird. My distribution looks exactly the same as yours. He might have a different center, and he might have a different distribution, but the percentage of data would be within the same parameters. And we measure that percentage of data with our standard deviation metric. Alright? We would say one standard deviation contains a certain amount of the data. Does anyone remember what it was?
68.
Yeah, 68.3. I'm jumping around here, let me skip ahead. So, one standard deviation will cover 68.3% of those trees. So I'm on the phone with this guy in China, I'm like, I measured standard deviation, and 68.3% of my trees are within one standard deviation of the mean. And he says to me, wow, the same thing happened when I measured my trees in China. That's because there was nothing weird going on in his population, there was nothing weird going on in my population, and they fell randomly into a normal distribution. We talked about some things that might skew a normal distribution last time. We looked at different incomes in towns. We said, well, what if there was a group of really, really rich people throwing off the distribution? We might have also had a discussion, which I don't think we had last time, but we could have had a discussion, such as, well, once people start making more money, they have more access to education, they're able to disenfranchise the poor people, and they're able to get even richer. All right? That might be a situation where we would have a really fat tail on the rich end of that distribution, and it would not be random chance who falls on either side of that distribution. But as long as nothing else is going on like that, then we might suspect that things would fall into this normal distribution. And we know things about this normal distribution. The 68.3 within one standard deviation is one of those things we know. We also know 95.5% of the data will fall within 2 standard deviations. All right, how do statisticians know that? Well, they did calculations exactly the same way you all did calculations with the binomial distribution. Remember this? Remember you actually did some of these calculations? All right, if I gave you more time, you could have done all of them. And if I gave you a lot more time, you could have done everything in between all of these. Well, statisticians have done everything in between all of these. And they're able to determine things like, what's the percentage chance that out of 20 coin flips you're going to have 15 or more heads? Well, you would add up the probabilities. You say there's about a 2% chance of that happening. Similarly, there's about a 2% chance of getting 5 or less heads. You might also be able to quantify things as what's the percentage chance that any one student who does this experiment is going to get 9, 10, or 11 heads. What's the percentage chance of that happening? Any one student, I send you home tonight, say flip a coin 20 times, what's the percentage likelihood you're going to get either 9, 10, or 11?
You went up to 3 and take the average, right?
No, just add up to 3. So what is it?
30.
No,
I'm sorry, I just said 9, 10.
9, 10, and 11. What's the probability when you do this experiment, you're going to write down 9 heads, 10 heads, or 11 heads? Well, it looks like about 46. Do you need one? Alright, so about a 46% chance. The point here is that this is predictable. And these are things statisticians know to be true if they can assume a normal distribution. They know that within this range, there's going to be a 46% chance. 15 or higher, there's going to be a 2% chance. Now I'm using actual numbers here, but when we standardize it, we put it all in a normal distribution, we know things like this. And me and the guy in China are on the phone like, wow, isn't that weird? 68.3% of my trees, 68.3% of your trees were all within one standard deviation of the mean. Alright, this is the great thing if we can assume that things will be in a normal distribution. And if they are subject to just basic laws of probability, random chance, law of large numbers, then things will fall into a normal distribution. Does that all make sense?
Yes.
Alright. So, let's do an experiment with this 20 coin flip example, and let's try to sample for the mean of this distribution. So, remember, when we talked about this, we said maybe we could send all 11,000 Mercy College students home and tell them to conduct this experiment, flip a coin 20 times, write down the number of times it comes up heads. Let's say we do that. We send all 11,000 Mercy College students home and we have them do that. But in this case, we don't have them come back and tell us what they got. It's just too hard to have all 11,000 students come back and report that data to us. Taking a complete census would be too difficult. But we want to know what was the average number of heads that came up for the Mercy College students when they did this experiment. So that's what our goal is. We want to find that number. Now, because we did the calculations already, what is that number? What is the average number of times that this came up heads in this pool of 11,000 students who did this? Was it 20? Was it 21? So 11,000 students went home and flipped a coin 20 times, and they wrote down the number of heads they got. If they had reported all the data back to us, and we crunched the numbers to determine the average number of heads that came up, what would it have been? 10. Yes, we've got one guess for 10. Do we like that? I like that. It would be 10. Yes, it would be 10. Right, that would be the average number of times that we would expect for heads, for students to, for students to come up with heads on this experiment. So if we were to report, if all those 11,000 students were to report back to us, tell us the number of times their experiment came up heads. One student would say it came up 11, another student would say it came up 9, another student might say 12. We add them all up, take the average. The average would be 10. Okay, so the true population mean in this case is 10. Let me write that down. And what's the symbol for population mean?
The mu.
Yes, population mean. All right, so this mu, population mean, equals 10. All right, so that we know to be true because we know the numbers. But let's say we didn't know this in this experiment. We had 11,000 students go home and do this. We heard people talking. We heard people talking in the hallway. One person said, oh, I got 10. Oh, I got 15. Oh, I got 6 heads. Oh, I got 9. We heard things. So we got a sense of maybe what it was, but we want to find out the sample mean. All right, and how do we notate sample mean? With a little X with a bar on it. This is our sample mean. Mean. This equals question mark. Okay, so we want to find, wait a minute. We don't know it yet. All right, we don't know the sample mean. Okay, how am I going to do this? All right, let me just keep talking and we'll work out those numbers as we go. Where was I? You want to know the population mean. We know it to be 10, but let's just assume we don't know it now. Okay? Is everyone with me there? Just a wink, nod. We don't know the population mean. And we're going to determine that by taking a sample mean. All right, we're going to take a simple random sample of a good sized number of students, say 30, and we're going to come up with a sample mean. All right, somebody give me an estimate. What do you think our sample mean is going to come out to?
15.
Just guess. Okay, 15, that's a good guess. All right, that's a perfectly reasonable guess. I was hoping maybe somebody would say something closer to 10, like maybe 10.7 or something like that. So that's going to work better for my example, but you're nothing to say nothing of your estimate. All right, 10.7. 10.7. So yeah, don't ask a question if you know the answer you're looking for. Don't give the students any option of giving a different answer if you know what the exact answer you want. All right. Okay. So we get a sample mean of 10.7. All right. I had a couple of experiments I wanted to go through on the next slide. Suppose we do not know the mean of the 20 coin flips distribution, so you conduct a simple random sample of 30 points of data. All right, what would be the most likely outcome for your sample mean? Now, our sample mean was 10.7. Question for you all, what would be the most likely outcome for your sample mean? Yeah, what's your name again, Ricardo? Andy. Andy. All right, why do you say 10, Andy? Yeah, all right. So the most likely outcome for our sample mean would be 10. The reason why it would be 10 is because that is the true population mean. The most likely outcome would be the correct answer. Right? Why wouldn't it be? Why wouldn't the most likely outcome for this experiment be the actual thing we're trying to determine? It would be 10, because that is the most common outcome. Maybe sometimes some of the people we would ask have 9, some of the people we ask have 11, a lot of the people we ask got 10, maybe one of them would have 12, another one might bounce out at 8. Most likely outcome would be 10. All right, next question. How confident are you that your sample mean of 10.7 would be close to the true population mean? Alright, so the true population mean, we know in the back of our heads is 10, but we're just pretending we don't know what it is. Alright, we got 10.7, and I want to ask you, just right now as statisticians, as statistics students, how confident are you that your sample mean of 10.7 is close to the true population mean of 10? I guess you know, because you know the numbers, it's like 0.7 off. How confident would you be if you didn't know that? How confident would you be that your sample mean is close to the true population mean? Well, I'm looking for two parts to this answer. One, I want to go through some analysis where we would say, yeah, we might be reasonably confident that our sample mean would come out to close to 10. But the second part is we're not able to quantify how confident we are. So how likely is it, remember we asked this before, how likely is it that any one student would get 9, 10, or 11 for the result of their experiment?
45%.
Like 45%. So of these 30 students we asked, there's a 45% chance that any one of them got 9, 10, or 11. So there's a good chance that most of the students are right in the center already. So there's a good chance that the answer to this question, how confident are your sample mean close to the true population mean, is fairly confident. Another thing that we might have working for us, suppose we were to look at results of 15 or higher. Now remember he said, what are the chances of any one student getting 15 or higher? What did we say that percentage chance was? Around 2%? Alright, so what are the chances of all 30 of our students in the sample getting 15 or higher?
Low.
Extremely low. So it's 30 people, all 2%. It's like 1 in a billion, 1 in a trillion billion, something crazy low like that. So maybe we might have one student get a really high number, which would pull our sample mean off and give us an unrepresentative answer. But the chances of all 30 students being really high and pulling it off, not that high. And there's also an equal probability if we get one student that's really high, we might get one that's really low and balance it out. So that's another point I would make that would make us say, we are fairly confident that our sample mean is in fact close to the true population mean. So, how many students were in this experiment overall? Do you remember?
30,000.
11,000. And how many were in our sample?
30.
30. Okay, so we did a sample of 30 out of 11,000 people, and I think we're comfortable saying that we're fairly confident that we have an accurate estimate. Right? Would you all agree with me? Yeah, I mean, isn't that kind of impressive? Isn't that kind of like a big step? Like just asking 30 people, and that's it. And we're fairly confident that we have a good estimate. You impressed by that? Yeah? If I want you to be? Fantastic. Alright, yes, question.
Is 30 seems to me like a small number for 11,000 people, but is it because the outcome is 50-50? You know what I mean? It's not like incomes where it could be.
Okay,
A
well
wide-
income could be a similar distribution as long as there's nothing weird going on in this town. The income distribution could look exactly like this.
But would you need a larger number or no?
Well, here's the thing. All right, if we ask someone who's really, really rich,
Right.
maybe one person would be really, really rich, but the chances of all 30 of those people being really, really rich and throwing off giving us an inaccurate sample mean, like you said, low, 1 in a billion.
Right.
The chances of us randomly asking 30 people who are all really, really poor and giving us an unrepresentative sample, also really poor. And the chances of most people being in the center of this distribution, also very high, or that is high, because it's normally distributed. Does that make sense?
Yeah, it's just gotta be truly random. Like-
It has to be truly random,
Okay.
yes. And in this case, we're looking at a normal distribution. Okay. So, we are confident and we are impressed that statisticians can say so much with so little, but the thing we cannot do yet is quantify how confident we are. We can't say I'm 80% confident. We can't say I'm 90% confident. We don't know how to do that. In order to do that, we need to take another step. So let's do this experiment a different way, or rather do a different experiment. Let's suppose we were to repeat this exercise of sampling 30 points of data, say 5,000 times. Okay, so we're going to take a simple random sample of 30 students. We're going to write the number, and then we're going to do it again. Take another simple random sample of 30 students. We're going to find the sample mean, note that number, and then we're going to do it again. And we're going to do that whole thing 5,000 times. And we're going to graph it. We're going to graph this on a frequency distribution, and we're going to call this frequency distribution sampling distribution of the sample mean. So, sampling distribution of the sample mean. Alright, we're going to have frequency or probability on the vertical axis. We're going to have outcome on the horizontal axis. Frequency. Alright, and so these outcomes, it's going to start at 0, go all the way up to 20. Right in the middle is going to be 10. Alright, so 15 or 5 would be here. 15 would be here. Alright, we're going to take a sample mean. The first time we're going to get 10.7, we're going to make a note, 10.7. Alright, we're going to do it again. We're going to get like 10.9. We're going to put a little X at 10.9. We're going to do it again. And we're going to get 8.7. Alright, every once in a while we're going to get something crazy like 15. Alright, we're going to make a note. And we're just going to keep adding this up. Alright, each time we get the same number, we're going to put the X on top of each other. We're going to do this 5,000 times. Alright, so same question.
Wait, isn't it 30 points?
So, okay, a sample size of 30. So we're going to take a sample size of 30, and we're going to take the average number of heads that those 30 students got.
Oh, okay.
And we're going to get something like this, 10.7. Out of our 30 students we sampled, we got a sample mean of 10.7. And that's just one time.
They did
We have
4,999 more.
Yeah, we have 4,999 more times to do that exact same thing. Alright, and we're going to keep doing it. Each time we do it, we're going to graph it. We're going to graph it on a frequency distribution. The outcome, the sample mean, how often we got it, frequency on the vertical axis. Alright, so same question I asked you last time. What do you think is going to be the most common outcome on this frequency distribution? 10. Alright, that's going to be the true outcome, the true population mean of 10, and that's going to be the most common outcome. What's your name again?
My name's Lisa.
Lisa, that's right. Okay, and what's your name again?
Charlene.
Charlene?
Charlene.
Sure. Like Shirley or Charlene?
Charlene.
Charlene, Lisa, sure. Okay. Alright, so our most common outcome, Lisa, is going to be what?
10.
10. Alright, why is our most common outcome to be 10?
But you just said that.
What? Because I just said, what? Tell me what? Alright, because that's the real answer. Alright, that is the population mean of 10. Alright, so most commonly we're going to get the right answer. Next question. What do you think this distribution is going to look like when we get done doing it 5,000 times?
Normal.
Normal. It's going to look like a normal distribution. Okay, because the most common outcome is going to be 10. Alright, every once in a while we'll get something a little bit more, or probably frequently, we'll get something a little bit more than 10. Equal probability to getting a little bit less than 10. Alright, unless there's some stigma involved in saying you got fewer coin flips. Hopefully the people who ask questions aren't asking the question in a way that makes the interviewee want to say something like that. So assume it's completely random and good sample. Is equal likelihood a little bit less, equal likelihood a little bit more, as a little bit less. Every once in a while we might get something crazy way out there. Similarly, we might get something crazy way down there the same way. Alright, so the most common outcome of this distribution, the mean of this distribution is going to be 10. It's going to be normal. Now, let's take a look at this question. How confident would you be that any one of your sample means would be within 1 standard deviation of the true population mean? So let me set that question up a little bit more. You have just done this 5,000 times. You've got a more normally distributed sampling distribution of the sample mean, and you have calculated a standard deviation for this mean. How confident are you that any one of these sample means, like 10.7, would be within 1 standard deviation of this mean?
Very.
Okay, very. This time you can actually give me a number. And the correct answer is 68.3. So you just took a sample mean of 30, and you are 68.3% confident that you are within 1 standard deviation of the mean of this, which is the same as the true population mean. How confident would you be that you would be within 2 standard deviations?
95.5.
95.5. Okay, so now we can answer that question with actual numbers. You took a sample size of 30, and you are 68.3% confident it's within 1 standard deviation. You're also 95.5% confident it is within 2 standard deviations. You can actually quantify it because of what you know about the sampling distribution of the sample mean. So let's look at the 2 characteristics of this sampling distribution of the sample mean. So the mean of this is notated with the mu and a little x bar. Alright, that's the mean of the sampling distribution of the sample mean. That is equal to the true population mean of mu. This also has a standard deviation. So standard deviation of the sampling distribution of the sample mean. Alright, we'll look at that right now. But we'll look at that with this next question. Do you think the standard deviation of this new distribution, i.e. this, is smaller, larger, or the same size as the standard distribution for the whole population?
Same.
So this is the whole population. This is the sampling distribution of the sample mean. So these are our 11,000 students in reality. This is our sampling distribution of the sample mean, where we take sample size of 30 and graph each one. Now, remember we said in the whole population there's a 2% chance of any one student getting 15 or more heads. What are the chances of all 30 students getting 15 or more heads? Very, very low. So in the sampling distribution of the sample mean, this outlier goes to astronomically small. How about for 14? Same thing. Alright, this outlier goes to astronomically small. Because all 30 in our sample would need to randomly be that high, there is a much less probability of it happening on the sampling distribution of the sample mean. So what that means is, this distribution is skinnier and taller, it's tighter, it's smaller. The distribution here is much less than the distribution here. So this bell curve and that bell curve are both normally distributed, but this bell curve is short and fat, this bell curve is tall and skinny. So this bell curve has a smaller standard deviation, and it is calculated this way. It is the standard deviation for the whole population divided by the square root of n, which is the sample size. So suppose we take a sample of 100. What's the square root of 100? 10. Okay, and square root of 100 is 10. So we would divide this standard deviation by 10, and we would get 1/10 the size of the standard deviation on the sampling distribution of the sample mean. So it's, you with me, Lisa?
Yeah.
Yeah, that was just a lot, so just think in real quick.
Okay, just take a breath. So the answer to this last question on the slide is smaller. So just circle smaller on the slides.
Did you print out the slides this time, or should we print them out before we come? I have them in front of me, that's why I knew that the bell curve was skinnier and taller, but
Okay.
I
Oh,
was cheating. Oh, you did? Oh, fabulous, thank you.
No problem.
Thanks, Professor.
Anybody else need slides? Yeah, I'll always have the slides here. Start with them.
Oh, nice, thank you.
Okay. So yeah, just circle smaller there. And then the two key things, the standard deviation of the sampling distribution of the sample mean is equal to the true population mean. This will be on the later slides, but just recap what was important about what we discussed. And the standard deviation of the sampling distribution of the sample mean is the standard deviation for the whole population divided by the square root of n. And there we have it. This is the sampling distribution of the sample mean. And those two concepts, the mean, sampling distribution of the sample mean, equal population mean. Standard deviation, sampling distribution of the sample mean, equals the population mean divided by the square root of n. For sample sizes of 30 or more. Statisticians like at least 30 to assume that the sampling distribution of the sample mean will be normal. If it's less than 30, statisticians are like, well, I can't promise you that this is going to be normal. If it's more than 30, then they say it will be normal. It will be normal, in fact, regardless of the shape of the population, of the parent population. All right, so this concept that Lisa was ahead of me on, the sampling distribution of the sample mean is taller and skinnier than the population distribution for the parent population. Because the chance of this kind of outlier in the parent population, all right, sure, there's a possibility of happening, the possibility of all 30 conforming to that, tiny, absolutely tiny. Okay, all right, how are we feeling on that? Are we feeling good on that? We need to take a breath.
Hurrah.
So
Relax for a
the
minute.
sample will be less than 30 then always, because the
So
population.
the sample
is
always
more
has to
than
be
30?
more than 30.
The sample has to be 30 or more,
Okay.
sample size. I feel like you might be confusing in your head sample size and standard deviation. Yeah, so sample size is 30.
Okay.
And then we take a sample size of 30, and we do that 5,000 times, we put it all on a frequency distribution, we get the sampling distribution of the sample mean.
I have a question.
Yeah, one second. Alright, so we put that all on a frequency distribution, we get the sampling distribution of the sample mean. And we know two things about that. We know the mean of that, which is what? Well, it's 10 in this case, but what's the general rule for it?
68.3.
The mean of the sampling distribution of the sample mean is equal to
You?
what's mu? Population mean. The mean of the sampling distribution of the sample mean is equal to the population mean. And what else do we know about it? The standard deviation of the sampling distribution of the sample mean is less. It's skinnier than the parent population. And there's a formula specifically for it. The standard deviation of the sampling distribution of the sample mean is equal to parent population mean divided by the square root of n. Does that make sense? What's your name again?
Eliana.
Eliana.
Ileana,
Iliana.
right?
Eliana.
Oh, Eliana.
Eliana.
Yeah.
Eliana. Okay. A question, Charlie?
There's always gonna be like 3 different brackets, right? Like the 68.3, the 95.5, and then there's like a 99.7.
Yeah, I wouldn't say there'll always be 3 different brackets, but those are just 3 things you know. That 68.3% of the data is within 1. 95.5 is within 2,
Yeah.
99.7 is within 3 standard deviations. And how do you calculate the standard deviation of this, Charlene?
Not really sure.
Somebody help out Charlene.
My tutor told me that, that's why he made like a little,
Okay, good. Somebody help out Charlene, tell her how we calculate the standard deviation of this?
Of the sample? Or,
The standard deviation of the sampling distribution of the sample mean? How do we calculate that?
that one, right?
Yeah, tell me.
Oh, it's the standard deviation of a sample,
The standard deviation of what? That's,
So the population.
yeah, help us out, Julio. It's the what?
standard
This is, what is this symbol
the
mean?
population.
It's up to you.
With the top one, we'll get the square root in it. This is, what's this symbol? Of what?
The population,
Divided by what?
square root of
Of what?
Simple sign.
Sample size, yes. Okay, so back to my original question. How do we calculate the standard deviation of the sampling distribution of the sample mean?
the population, deviation divided by square root of n.
Yeah, yeah, yeah. That's how we do it. So we can calculate the standard deviation of the sampling distribution of the sample mean with this formula. Once we have this formula, we know what the likelihood of any one sample mean of 30 is going to be within one standard deviation of the mean. And how likely is that, Charlene?
68.
68.3. All right. How you feeling, Eliana?
A little bit better.
Okay. Alright. Yeah. So, what should we do here? Should we ruminate on this for a minute? Should we go on to the next slide? Should we ask a question about the sampling distribution of the sample mean? What's your name again? Francisco. Help us out. Give us a good question to slow us down here. Otherwise, we have to go on to the next slide. Go ahead.
You want to give you a question?
Yeah. Ask a question.
Professor, I think to visualize it better, I think if you plug the numbers into, those formula, I think at least it will help me out to, make better sense.
Okay. So, what's the true population mean? 10. Okay. So what's the mean of the sampling distribution of the sample mean going to be?
10.
10. Okay. Good. All right. Just suppose the standard deviation of the true population was 5. Okay. And suppose we did a sample size of 30. What would be the standard deviation of the sampling distribution of the sample mean? I'll give you a hint, you probably can't do this in your head. 5 divided by the square root of 30. .91. Okay, yeah, so 0.91. Alright, I like it. So the standard deviation then is going to be 0.91. The mean of the sampling distribution, the sample mean, is going to be 10. So, let's see.
So the number here is the total population standard deviation, and we're figuring out the sample size of it? What are we figuring out?
Okay, alright, so we'll just run through this again. So, our goal here was to determine the true population mean. And in order to determine the true population mean, what did we do? We took a sample. What did that sample come out to? 10.7. Okay. And we want to ask the question, how confident are we that that is reasonably close to the true population mean? We know in the back of our head that the true population mean is 10. And it turns out with the sampling distribution of the sample mean, we can quantify exactly how confident we are that any one sample is within a certain number of standard deviations of the true population mean. So if I were to take that sample of 10.7, how confident could I be that that sample is within one standard deviation of the true population mean? Eliana?
What is it, the percentage that we got?
Help us out, Charlie. How confident could I be that that sample is within one standard deviation of the true population mean?
68.5.
Or 68.5?
Wait, sorry, 68.3.
Yeah, 68.3. Alright, so you know what, I think we kind of got the general idea. We do, right? We've got the general idea.
Yes, it makes sense.
Okay. Alright, so, yeah. Are we feeling okay on this sampling distribution and sample mean?
I'm going off track real quick. Is this gonna be the hardest class that we take in our MBA?
Yes.
Cause this is like freaking hard.
Yeah.
You're like a doctor in this, but like we're like in first grade in this. So like this is college for you, first grade.
Yeah, yes, I think this is the hardest class you will take
Yeah.
in your MBA career.
Oh,
Oh
God, I hope
baby
so.
Jesus.
I hope so. Alright,
I didn't figure out foreign language
let
Sample
me,
distribution of the sample mean, come on. You don't talk this
You
language
know.
every day?
how should we do this? Let's just go back. Let's do this slide and this slide again. Okay, you wanna do these two slides again? Alright, let's do the two slides from the beginning. Alright. So suppose we did not know the mean of the 20 coin flip distribution. So we conducted a random sample, 30 points of data. We got, say, a sample mean of 9.4. Alright? How confident are you, no wait a minute. What would be the most likely outcome for this sample mean? We got 9.4, but what's the most likely outcome? What would it have been before we got 9.4?
10.
Yeah, it would be 10. Why wouldn't it be 10? Because that's the actual answer. The true population mean is 10, so the most likely outcome would be the real answer. Second question, how confident are you that this sample mean, 9.4, is close to the true population mean? Fairly confident? Yeah, I think we decided that we're fairly confident. The reason we said we're fairly confident is because, look at this distribution. How likely is it that we would get 9, 10, or 11?
Likely.
40%. So any one of those 30 students, there's a 45% chance they're going to say 9, 10, or 11. So most of our students who respond to this survey are going to be right in the center. And they're going to give us an accurate representation of the true population mean. Right? How likely is it that any one student gives us 15 or more? Well, 2%, right? Okay, so it could happen. It might happen in our sample. But are all 30 of our students going to say 15 or more?
No.
Tiny percent chance of that happening. So in answer to this question, how confident are you that your sample mean would be close to the true population mean? I think we went through a discussion where we said we would be fairly confident for those two reasons. That out of a population of 11,000 students, we sampled just 30, and out of that, we're pretty confident. We're feeling pretty good that we've got a reasonable answer. This 9.4, that's a reasonable answer. Okay, so we like that? All right. We can say reasonable answer, but we can't say how confident we are. We can't say I'm 68.3, we can't say I'm 100%, we can't say I'm 90%. We can't quantify it whatsoever. And what we want to do is find a way where we can quantify it. How can we give a number of how confident we are? So let's do this experiment again, or do a slightly different experiment. Let's suppose we were to repeat sampling these 30 points of data 5,000 times. After each sample, we plot the sample mean on a frequency distribution, and we call this distribution the sampling distribution of the sample mean. So, sampling distribution of the sample mean. Alright, so what goes on the vertical axis?
Frequency.
Frequency, I like it. Frequency. What goes on the horizontal axis?
Outcome.
Outcome. Alright, out. Alright, what's the lowest number on our outcome? What's this number here?
0.
0. Because it is possible that the outcome could be 0 heads.
Correct.
Extremely small, but it's possible. There's also a possibility the sample could come out to 20. That's possible, very small. The middle is going to be 10. Alright, so we're going to take a sample mean, like we did here, and we get 9.4, and then we're going to write 9.4. We're going to put a little x by 9.4. What are we going to do next, Ileana?
Fill it in.
Well, we did it once. How many times are we going to do it? Okay, so walk me through. What am I going to do now? I've just one sample mean. What do I do next? I take a sample of size 30,
Oh.
right? And then what do I do?
Get the next.
I calculate the sample mean, and it comes out to, say, 10.1, right? And then I write a little check mark by 10.1. Alright, I'm sorry, it was one of those like simple questions that was confusing because you were lost in my thought process. Now what do? I do it again.
Yeah.
I get a sample mean, I put a little x, I do this 5,000 times. Okay? I put a little x every time. What is the most likely outcome for what am I going to get most of the time? What's the most likely sample mean I'm going to get? 10. Okay, so 10 is going to be the highest point of this distribution. Alright, what is this distribution going to look like?
Normal.
Normal. Why is it going to look normal?
It's going to follow the population.
It's not that it's going to follow the population, because we'll find that it doesn't matter what the population looks like. It's going to be normal because it's completely random. Because the most common outcome is going to be here, and then there's an equal probability of getting a sample mean a little bit higher than 10 as a little bit lower than 10. There's an equal probability of getting a sample mean of 12 as a sample mean of 8. Those things are both the exact same likelihood. So this is going to look normal. It is going to be normal. So this is our sampling distribution of the sample mean. It's going to have a mean, sampling distribution of the sample mean is going to be equal to the true population mean. So the mean of this normal distribution is going to be equal to the true population mean. And it's going to be normal. Next question. How confident would you be that any one of your sample means would be within one standard deviation of the true population mean? So one of our sample means, let's just say it's 10.3. How confident would you be that that is within one standard deviation of the true population mean?
68.3%.
You'd be 68.3% confident. Because you know that in any normal distribution, 68.3% of the data, 68.3% of the data falls within one standard deviation of the mean. And we know that the mean of this is the true population mean. So we have a sample mean of 9.4, and I am able to say that I am 68.3% confident that that is within 1 standard deviation of the true population mean. And our goal here is to determine what the true population mean is. We want a number. We want to go to our boss and say, here's the true population mean. But instead we're going to go to our boss and we're going to say, this is a sample mean of 9.4. I'm 68.3% confident it's within 1 standard deviation. Maybe our boss wants a higher level of confidence. So what do we say in that case, Charlene?
Negotiate. From 95%. Within 2.
Go ahead, Francisco?
Yeah.
Yeah.
You'll be 99.5 confident within
95.5, yeah. You say, okay, you want a higher level of confidence? Fine. I'm 95.5% confident that it's within 2 standard deviations of the mean. You want to be even more confident than that? What do you say, Susie?
I'm, what, 99, whatever it is.
99.7.
7% confident that it's within 3 standard deviations of the mean.
Yeah. Yes. Okay. So that's our sampling distribution of the sample mean. And then the last thing I asked is, do you think the standard deviation of this sampling distribution of the sample mean is smaller, larger, or the same as the population?
Small.
So this is the population, this is the sampling distribution of the sample mean.
Small.
And it's much smaller because the chances of getting heads 15 times for any one student, 2%. The chances of all 30 students getting heads 15 times, tiny. So this sampling distribution and sample mean is going to be skinnier and taller. It's going to have a tighter confidence interval. So when you go to your boss and you say 1 standard deviation, it's going to be a smaller number. You're going to be able to give your boss more precise information. All we need to do is add 3, subtract 3, or add 2.7, subtract 2.7, whatever it is. Okay. Eliana.
Much clearer.
All right.
Thank you.
You bet, you bet, you bet. All right. So sampling distribution of the sample mean is the probability distribution, which we did, of all the values of the sample mean with sample size of n is taken from a given population. To produce this, we would at least conceptually generate all possible sizes. We would do this infinite number of times. We would put this in a frequency distribution. And for large enough sample sizes, size of 30 or more, this is normal. That's the key. This is normal. We can assume it's normal. It has certain qualities that we went over, and then we're on the slide before. The mean of the sampling distribution of the sample mean is equal to the true population mean. The standard deviation of the sampling distribution of the sample mean is smaller than the population standard deviation. And it's smaller calculated by dividing it by the square root of the sample size. Statisticians call this the central limit theorem. Don't get confused by this. This is just restated what we've just gone over with the sampling distribution. Yes, Susie?
Why don't they come up with 30? Like 30 being the number that under 30 they can't be that confident, but over 30 they're much more confident that's gonna.
Honestly, I don't know. They just did through trial and error, and they said, you know, when we do sample sizes of 29, they must have had some calculus equation which said 29, it may not be normal, or it's getting normal. Sample size of 25. Yeah, they went through something very complicated and proved it somehow. And we just went through an intuitive, well, if you ask 30 people, what are the chances of all 30 of them getting a really extreme example? Really, really tiny.
Right.
So that was good enough for us now, but statisticians went through a much more rigorous proof and decided 30 was the right number. Good question. All right, so central limit theorem. So it's this thing. As the sample size increases from 2 to 5 to 10 to 30, then the distribution of this sampling distribution of the sample mean approaches the bell curve of normal distribution, regardless of the shape of the parent population. So our parent population with the coin flip, that was normally distributed. This works whether the parent population is normal or not. Doesn't matter. this will still work. As long as we have sample sizes of 30, the sampling distribution and the sample mean will be a normal, nice bell curve. Now, if the parent population has a normal distribution, then the sampling distribution and the sample mean has a normal distribution for any sample size. If the parent population is normally distributed in a bell curve already, then we don't even need a sample size of 30. We could take a sample size of 5 or 10, and the sampling distribution and the sample mean would be normally distributed. That'll come up later, just towards the end of class. All right. So let me I'm going to skip over this slide, and I'm going to go to this slide, and say, remember this town where we had a mean income of 60, median income of 60, mode income of 60? All right, and we want to find the average, the mean population in this town. How are we going to do it? Well, we're going to take a sample of size 30 or more, and we're going to get a sample mean, and it's going to follow the rules that we learned about with the sampling distribution and the sample mean. We can say I'm 68.3% confident that that sample mean is within 1 standard deviation, etc., etc. And it turns out that even if we go to this town that had a weird distribution, a positively skewed distribution with a bunch of rich people, it had a mean of 80. It turns out that this works as well. This same thing works even though the parent population is not normal. The reason it works is because this still has a mean, and that's all we want to know. We want to know what the mean income in this town is. We don't need to know that it's different from the median and different from the mode. All we need to know is what is the mean. And we're going to ask 30 random people. Maybe we're going to get these poor people, maybe we're going to get some of the really rich people. Sometimes the rich people are not going to be in our sample, sometimes they are. But on average, we're going to get a normal distribution, and it's going to center around the mean of the whole population of 80. So it turns out this works even if the parent population is not normal. Does that make sense? Mm-hmm. And let me go back to this slide. So these 3 shapes are the parent populations. All right, this is a really weird distribution. This is some town where we've got an equal number of people making, 10,000, 10,001, 10,002, whatever it is. This is a weird where we've got a bunch of rich people, a bunch of poor people, not many people in between. They still have an average. All of these three populations still have an average income. And we want to find out what it is. So let's take a sample size and let's put it on a frequency distribution. These 9 distributions here, these are sampling distributions of the sample mean. This row is with sample size 2, this row is sample size 5, this row is with sample size 30. So as we take a larger sample size, regardless of the shape of the parent population, the sampling distribution of the sample mean looks normal, is normal. Does that make sense? Okay. Good. Good. So this is going to be our basis for confidence intervals. So because we're able to say I'm 68.3, 95.5, that's going to give us confidence intervals. So we're ready to talk about confidence intervals? You ready? Ready, Lisa?
I'm ready.
All right. So let's look at this example. Suppose we're trying to estimate the average cost of an MBA program in the whole population. We aren't able to research every single MBA program, so we take a simple random sample. We calculate a sample mean of $43,000, and we calculate a standard deviation of the sampling distribution of the sample mean at $2,000. Please state the interval estimate for the average cost of every MBA program. Use a 95.5% confidence level. So why don't you all start working on that? I'll erase this half of the board. Give us some room to work with.
So, are we using that formula right there? The average is the mu, so it's for the flow rate. Is that the formula that you just erased?
No, you're not gonna need to use the formula. You're just gonna need to use some intuition.
Intuition.
Yes. So, our sample mean is $43,000. Alright, and we have a standard deviation of the sampling distribution of the sample mean at $2,000. So, we want an interval, and this interval estimate is gonna be an amount. It's gonna be like, you know, $41,000 to $46,000. Or, you know, $39,000 to $49,000. It's gonna be a range. And I want you to tell me that you're 95% confident that that range contains the true population mean for the average cost of an MBA program. The 95.5% chance that you've got it right. Anyone think they have an answer here?
Do you have a definition of the sampling distribution? What is it called? The sample, what page is it on? Right, it's 12.
It's on slide 17. Alright, Andy, help us out. What kind of range would you give us if you wanted to be 95.5% confident? Okay, so what would be the lower end of that range?
Maybe
Wait, aren't we just
below
deducting?
40, so 30, 40?
40?
Because if you're within one standard deviation, it will be less than 41. No?
Okay, so you want two standard deviations.
So
What would be
39,
two standard deviations below 43,000?
39.
I like it. So 39,000 would be the low estimate, and what would be your high estimate?
47.
Okay, 47. Yeah, so this is the answer I'm looking for. So, if we want to be 95.5% confident that we have captured the true population mean, or that this interval contains the true population mean, then we need to go plus or minus 2 standard deviations. What do you think, Charlene?
Go plus.
Well, this is the range, this is the confidence interval. So what you're gonna say to your boss is I'm 95.5% confident that the true cost of an MBA program, the true average cost of an MBA program, is between $39,000 and $47,000. Question, Susan?
So you'd only be 68.3% confident that it would be between 41,000 and 45,000. Okay.
What's your name? Nadine? Oh, this is your first time here, right? What's that? Okay, good to meet you, Nadine. Alright. So, I am 95.5% confident that the true population mean for the cost of an MBA program is between 39,000 and 47,000. And if I wanted to be 68.3, I would do what Susie said. So these are confidence intervals. I've got some pictures that might help us. So let's sample for this cost of an MBA program. All right, let's take a sample mean of size 30, and let's do it not 5,000 times, let's do it 5 times. Each of these little X bars, that's a different sample mean. Okay? If we were to do it 5,000 times, then we would get a distribution that looked like this. Sampling distribution of the sample mean for average MBA cost. Alright, but now someone else has already done that. We're just going to do it 5 times. Alright, our first sample mean, we're going to get, whatever it is, we're going to plus or minus 1 standard deviation. Okay, so does that interval, plus or minus 1 standard deviation, contain the true population mean? The true population mean is the mean of the sampling distribution of the sample mean. So this is sampling distribution of the sample mean, and the center of this equals the true population mean. So the true population mean can be represented with this red line. So I take sample x bar 1, and I get some number, and then I add 1 standard deviation to it and subtract 1 standard deviation to it, and I say to my boss, here's my confidence interval. Does my confidence interval contain the true population mean? Yeah, it does, because it crosses this red line. Okay, so it happens. So what I give my boss is correct. I said I was 68.3% confident, and it so happens, boom, got it. Nailed it. Alright, so I do it again. Or somebody else in the office does it. They do a different sample. And they get x bar 2. They do plus or minus 1 standard deviation. They give this to their boss. They say, I think this contains the true population mean. I'm 68.3% confident of that. Does it?
No.
It does not. Alright, how about number 3? Does it?
Yes.
How about number 4?
Yes.
How about number 5?
No.
No. Okay. So, what are the chances any one of these sample means with plus or minus 1 standard deviation is going to contain the true population mean? 68.3. Yeah. So there's a 68.3% chance that any sample mean would fall in this range. And if you add 1 standard deviation, 68.3% of those times, that interval is going to contain the true population mean. If you want to be a little more confident, then you would make your confidence interval 2 standard deviation wide. 2 standard deviation wide. 2 standard deviations wide. How often is that piece of paper with the range written on it that you give your boss, how often is that going to be correct? 95.5. So just like these. It's like this one's correct, this one's correct, this one's correct, this one's correct, this one's not correct. That only happens 4.5% of the time. And 99.7, if we want to do 3 standard deviations, that works too. Okay, how are you feeling on this? We've got confidence intervals. And we know we base confidence intervals on the sampling distribution of the sample mean. Alright, a couple terms that we already know, that we've already started using. I just want to put them in context. This sample mean, we're going to call that our point estimate. We refer to sample mean as the point estimate for the population mean. So this 9.4, that's our point estimate for population mean. Later we'll do a point estimate for the population standard deviation. We haven't gotten there yet. Rather than settle for this point estimate, we're going to construct a confidence interval. We're going to take this sample mean plus or minus some amount, and we'll call this a confidence interval, and we'll say how confident we are with that interval. Here's our formula for that. It should look somewhat familiar. This x bar, that's the sample mean. This little part right here, what is that? Not the z, don't worry about the z for a minute. Just this part right here, what is that? I can't hear. Francisco?
Is the standard deviation of the population divided by the root square of the sample
Yeah, it is. And what does that equal?
equal to the sample, the standard deviation of a sample mean?
Yes, the standard deviation of the sampling distribution
Sample
Sampling of the sample.
of the sample mean. Okay, so this is our standard deviation metric. It's the standard deviation of this. And we know it's equal to the population mean divided by the square root of the sample size. So we're gonna plus or minus some number of these. Alright, and z is the number of standard deviations. Remember we gave people a z-score last time, so Michael Jordan has a z-score of 2.3. That means he's 2.3 standard deviations above the mean. So if we want to go 1 standard deviation above the mean, we're going to multiply 1 times this. If we want to go 2 standard deviations above the mean, we multiply 2 times this. 2 above, 2 below. We'll maybe do something like that. So that's it. That's it. Let me ask you how we would determine that z value. Let's look at this for a minute. So suppose I want to be 95.5% of my confidence interval. What do I put in for this z value?
2.
2. Outstanding. Let me write that. So 95.5, I put in a z value of 2%. Okay. So we know the rest of it, right? We know the sample mean, we calculate this by sampling for it. And we know how to calculate this, population standard deviation divided by sample size. What if I want to be 68.3% confident? What do I put in for z? 1? Okay, what if I want to be 95% confident? What do I put in for z?
2.
Go ahead, Susie.
1.9 or something, right under 2?
That's the first step. That's the answer I'm looking for. It's something less than 2, right? Because I don't need to be as confident, so I don't need to go as far. So it's something less than 2. In order to get the exact number, we need to look on the z table. And here's how it works when we look on the z table. We say, hey, I need to be 95% confident. So what are the chances of me making a mistake? If I'm 95% confident, what are the chances of me getting it wrong?
4.5? 4.5.
5%.
5%.
5%. So if I'm 95% confident, the chances of me getting it wrong, 5%. Now, there is an equal chance I could get it wrong by being too high or being too low, right? So if I'm 5% chance of getting it wrong, then there's a 2.5% chance of a really, really high frequency of a really, really high sample, and there's a 2.5% chance of a really, really low. So I need the z-score that separates the upper 2.5% from the bottom 97.5%. Alternatively, I could look for the negative z-score that separates the bottom 2.5% from the upper 97.5%. If you look on the graph I gave you last time for class 1, you would need to look here because you only have positive z-scores. So you want the z-score for this, which separates the upper 2.5% from the bottom 97.5. And if you remember, you're going to look in the center of the z-score for 0.975, and you're going to see what z value that is. We're going to give that a shot?
Wait, we're looking for 0.975?
Yes, you're looking in the center for 0.975.
0.835.
0.975.
What's the z value, Susie?
So it falls in between 07 and 08. right, 9.975?
It's not the answer I'm looking for.
And .07.
Go ahead, Lisa.
.18.
0.18?
And
Not the
point-
answer I'm looking for.
One
Eliana?
1.96.
1.96 is the answer I'm looking for. 1.96. So see if you can see 0.975 in the middle and convince yourself how that is going to be a z-score of 1.96. So look at, where's 0.975 in the middle here?
.975.
Okay, 0.9, that's it, 0.975. So that's 1.9 and it's 1.96.
1.96. Oh,
Yep.
that's how you got that number. All right,
Exactly.
thank you.
Exactly. Does that make sense, Lisa? You find it?
That's Susie. I'm the
Susie.
second.
Susie, sorry.
No.
Alright, so. So, find 0.975.
Alright. Is that it? Yeah.
No, that's 0.834.
Oh, okay, I get it. There.
Yes, okay. So
That's
that's
what you're looking at.
1.96.
Right, okay.
Yes. Alright, does it make sense? I'll show you how to read the Z table. Okay. Alright, so great. So this is 1.96. 96. Sorry. 1.96. Okay. What if we wanted to, let's do one more. What if we wanted to be 90% confident? What would be the Z value we would use for 90% confidence level? So if we need to be 90% confident, what are our chances of getting it wrong?
10%.
10%. What are our chances of getting a really, really high sample mean?
5%.
5%.
And 5% chance of getting really, really high, 5% chance of getting really, really low. So 5% chance of making a mistake down here, 5% chance of making a mistake down here. So I want to know the Z value that separates the upper 5% from the bottom what percent? 95. So the upper 5% from the bottom 95%. So I'm going to look on the Z table for 0.95. Who said that?
1.65.
Yeah, perfect. 1.65 is the correct answer. You feeling okay on this? Alright, let's do an example. Let's look at, on page 248, exercise 7.4. Actually, let me, does anyone, maybe can I, does everyone have their book with them?
I do here.
I can, this is gonna take me a second, I can pull this up online.
You want my book?
Who has their book? Raise your hand if you don't have your book with you. Okay, yeah, let me pull it up online so everyone can see.
Oh.
248. Okay, so, we want to estimate the average time cars stayed on the lot for these BMW 5280i, these BMWs last year. So, we wanna know how long they stayed on the lot on average. I guess you can't even read that, can you? Can you read that? Oh, sorry, alright, well, I guess that's the best I
You
can
can
do.
probably zoom in.
I did zoom in. When I zoom in,
Oh, there you go.
oh, okay. There we go, sorry about that. Good call, Lisa. Alright, so we want to estimate how much time these cars stay on the lot. Suppose we don't wanna ask every single dealership, because the car dealers just lie to you anyway. We wanna take a sample of 60 BMW dealers, and we wanna figure out, our sample of 60 cars sold last year, and figure out the average time they were sold, and we come up with a sample mean of 97 days. So, we want a confidence interval, 95%, for the average time spent on the lot for every single BMW sold last year, for the entire population. Assume we know the standard deviation for the population to be known at 22 days. How are we going to solve this problem? Let's see if I can. Okay, there it is. You can all see it, but you can't see the answer. So, why don't you start working on the answer? So we got a sample mean of 97. Alright, we know the population standard deviation is 22. Alright, so how do we construct this confidence interval? Someone remind me. Francisco, go
Use
ahead.
the formula.
Use the formula. What's the formula?
It's x bar
Yes.
plus minus.
Plus or minus
2 or the
Z, yes, times what?
times the
Standard deviation of the sampling distribution of the sample mean. Okay, so how do we calculate the standard deviation of the sampling distribution of the sample mean?
it's 22 divided by the square root of 60.
Yes. So we take 22, the population standard deviation, divided by the square root of the sample size, which is 60, and what do we get? What does that come out to? 2.84. Okay, good. What is the Z value we use for 95% confidence?
I'm sorry, what was
What is the Z value we use for 95% confidence?
it?
Francisco said 2, and I looked at him like he had 4 hits.
1.9.
1.96 is the correct answer. Okay, so what do we do next? Well, we take 97 plus or minus 1.96 times 2.84. And what do we get on the low end?
Can you switch over?
Sorry.
Thanks.
Rebecca.
On the low end.
Oh, yeah, Susie, you have the low end?
91.4.
You agree, Andy?
I have a question.
Yes.
When you say 95% confidence, you go to the ZTO and look for 95%?
You look for 97.5%. Yeah, so if you're looking for 95% confidence, that means there's a 2.5% chance you could be wrong here. You got it?
Yeah, I got that.
So does anyone agree or disagree with 91.4 on the low end?
With that equation, that's the answer.
Okay, what do you got on the high end?
102.5.
102.56?
Yeah.
Alright, looks good. 91.4 and 102.56. Alright, so how do we present that information to our boss? What do we say? It starts with, I am 95% confident.
That, whatever it is, falls.
That's right, you can, yeah, it's good for now. Whatever it is,
Two
falls.
standard deviations. Within 2 standard deviations, I mean, yeah?
Now, falls within 1.96
Oh, okay.
standard deviations,
96, okay.
and not of the mean. Alright, so,
Of the sample of
okay, so the statement you make, you say I'm 95% confident that the true population mean for all BMWs sold last year is between 91.4 and 102.56. We can stay on that for a while, Eliana, if you didn't like it the first time. I am 95% confident that the true population mean for all BMWs sold last year is between 91.4 and 102.56 days. What do you think, Lisa?
I'm thinking that I need a tutor for this class.
We can work on it. We can
Have
get there.
schedules.
It's so
So,
frustrating. Like,
It really is, it's a lot.
I don't even know how to calculate it. I need someone to sit with me and like show me how to do it on a calculator and how to pull these numbers. Like, just,
well, don't worry about the calculations for right now. Just worry about the intuition. Now, Charlene, this is going to be tough because you missed the critical part where we figured out how
It's
to
pizza lad, sorry.
calculate 1.96. But what we learned while you were gone is that we want 1.96 standard deviations for 95% level of confidence. We want 2 standard deviations for 95.5, which you already knew. But now we know we want 1.96 for 95% confidence. So we took a sample mean of these 60 BMWs and found out the average time they spent on the lot was 97 days. That's our point estimate. If we had to guess, gun to our head, how long do you think the average for every BMW stayed on the lot last year? I'd say 97. Are you with me so far?
Yeah.
That's my estimate for the population mean. The population mean of average time BMW spent on the lot. I guess 97. But that's just one number. I want a range, and I want to be able to say I'm 95% confident that that range contains the true population mean. So that means I need to go plus or minus 2 standard deviations on this sampling distribution of the sample mean. How do I calculate standard deviations on the sampling distribution of the sample mean? I take the population mean divided by the square root of n, and that comes out to 2.84. So,
Wait, can I stop you right there real quick?
Yeah,
When
yeah.
I did that, I got 3.510, so did I do something wrong, 22?
yeah, you did something wrong. I can't do calculator tutoring, so just concentrate on, I can help you with that after class, but I wouldn't worry about the calculations right now. Just make sure you understand the intuition. So, but do you understand, like, how we got that? That's 22. What is this 22? Where do we get that number?
The population.
Population standard deviation, right? And then we divide that by the square root of the sample size. And it came out to 2.84. So we need to go 1.96 of these above and 1.96 of these below our sample mean. And that's going to give us a range. And we're going to say we're 95% sure, based on what we know about the sampling distribution of the sample mean, that the true population mean is in that interval. Okay, question? Or is that a thumbs up? Yes. So let's take a break. We deserve it. Let's come back at 8:20.
It's 8:08 right now.
Okay, yes. Let's come back at 8:20. And then we'll do some more examples on the same thing. More examples on this. We're not gonna move on. We'll just try to ingrain this, and we're gonna come back at 8:20.
What?
I went to one today, it's good.
For, is that just for this class?
Go ahead.
No, it's just like-
No, it's on Google, just search financial calculator, and see what it means.
You want
The
to
income calculation.
It's everything.
I had a bag of chips.
Thank you.
Sushi for lunch. I asked him to make me a salad and the stupid jerk was like, oh, we're closing right now. I'm like, I want.
So, page 20, or page 248, number 20, I've got it up here. We're gonna start working on that. If you need to read this, you can. Otherwise, you can read it in your textbook. Should we start working on it together? Or?
So, yeah, the Z-score is 1.96 again?
That sounds right. Sounds right. Alright, do you need a few more minutes working individually, or should we do it together? You need more time, Ellie?
Yeah.
Okay. Lisa, do you have a textbook, or if you don't have a textbook, you could look up there. And I would just work on working out the formula, like don't actually do the calculations, just like write out the steps that you would take.
Okay.
let's do it. So what is our goal here? What are we trying to accomplish with this problem?
To get the 95% confidence.
Yeah, 95% confidence of what?
Of the average time spent online.
Yeah, average time spent online for the whole population. So our goal, I would say, is, maybe we can do that later. So our goal is to try to find the average time spent online for the whole population of these teenagers. So from age 12 to 14, what's the average time that they spend online? All right, we can't ask every single teenager. All right, it's hard to imagine asking every single teenager. So we take a sample. All right, what's our sample size?
754,
Okay, and what do we get for our sample mean?
8.2.
All right, so that's our point estimate of how much time we might think these teenagers spent online. All right, but we don't want just a point estimate, we want a range. And we want to be 95% confident that that range includes the real mean, the real amount of time that teenagers spend online on average. So, we know the population standard deviation is 2.6. If we want a 95% confidence interval, what's our z value? How many standard deviations above and below the population mean do we need to go?
1.96.
Yeah, 1.96, excellent. All right, and what is our standard deviation metric that we're going to use? So what's our standard deviation of the sampling distribution and the sample mean?
22.6 over.
Square root of
Over
something.
the square root of the total number.
754.
Excellent. All right, and someone who feels comfortable with the calculator can tell us what that is. If you don't feel comfortable with the calculator, just make sure you have the intuition. What's the answer we get to that?
0.954.
Okay. Anyone agree or disagree with that?
It's a 0.09, sorry.
Okay.
Yeah.
0.09554?
Yeah.
Okay. Alright, so that is our standard deviation. So we need to go plus or minus 1.96 of those. So our confidence interval is going to be 8.2 plus or minus 1.96 times 0.0954. And that's it, right? All we need to do now is just crunch that out. And we'll have a confidence interval, a 95% confidence interval. So, did anyone get that far?
Well, that number is not correct.
I have a
I
different,
got 8.01 to 8.3.
Wait, which number's not correct? Who said the number's not correct?
I got a different number
I
for
got
that.
8.39.
The other one, the standard deviation.
Oh, for this?
Yeah.
For this?
Yeah,
What'd you
yeah,
get, Rebecca?
8.39.
8 point, what'd you get, Francisco?
maybe a 0.946.
0.946.
4.6, yeah.
0.946. Maybe did you forget to divide by the square root, Rebecca?
Not the zero, just 0.9.
Yeah, I messed up.
How do you get the 1.96?
Okay. Alright, so, alright. So we like this, 0.948 for our standard deviation metric. Okay, so we're happy with that correction. So now all we need is 8.2 plus or minus 1.96 times 0.948.
I got 8.01 to 8.39. Is that right?
8.39?
Around that, yeah?
Okay. I could be okay with that. What do you think, Rebecca?
8.2 times 6 times
more inclined to believe 10, because Andy,
Oh,
this
yeah,
is
yeah.
this is
Okay.
1.96 times almost 1.
Okay.
So that's close to 2.
Yeah, 1.85.
Yeah.
And then how do you get the plus minus?
That's the equation.
Oh,
You add it and then you subtract.
So you,
just add.
oh, I get it. You mean, then you
Either higher or
add that or
lower.
you minus it and that's what the
Right.
variation is?
Yeah, the confidence interval, yeah.
Okay.
Alright.
Oh, jeez.
First smile all.
I know, I'm getting so pissed off.
Alright. So what did Rebecca, what did you get for this? 10.05, what did you get for the low?
Minus 8. Equals
So like,
6, minus 6.34?
6.34.
Oh, no, minus.
alright, I feel like that's wrong, but,
You
Yeah.
subtract the,
does anyone have that,
So 1.96
the answer in the back of the book?
times 0.948 equals
Is this
minus-
right? Let's someone check
No, I
this.
think, I
1.2
feel like
equals-
my first answer was correct.
Yeah, that's what I feel like too.
0.0946.
Mhm.
I don't know.
It's,
Point 0.9. I'm an auctioneer up here.
no, it's not 0.0946, is it? It's 0.946.
Alright.
Do you
We're
need,
gonna
you wanna
final
borrow my
answer.
calculator?
Can we get a,
2.6 divided by.
After you get the.
you take the z-score times the standard deviation and subtract it.
Yes.
So 8.2 minus 1.96 times whatever we decide this to be. And we're still working out what we decide this to be.
Square root.
Alright, so do we have a confident answer on this? Susie, you're comfortable with this? The answer to be what Susie?
I come up with 0.9469, so 0.947, I think.
Okay, fine. So this is the answer. Yeah? Is that in the back of the book? Says that's the answer?
That's what I.
Can anyone look in the back of the book? Let's see if that's right.
Why don't you just tell us how to do it on the calculator? I'll just feel better that way. 2.6 over the square root of 554. How did you punch it in? Just tell me.
So I would punch in, my calculator would probably be different than yours, so I would punch in 574 square root.
754.
754 square root.
754 square root,
Uh-huh. Where'd you get it?
27.45.
Alright, so write that down.
Okay, sure. 27.45. Go ahead.
And then clear it.
Clear it.
2.6
2.6
divided by that number.
divided by 27.45. 0.0947.
Okay, I like
It
that.
comes out to the same numbers anyway.
Point
Let's look at them and see.
Same decimal
0.0947.
point too.
Yes.
0.0947. Okay,
There you go.
I like that better. 0.0947.
It comes out to the same answer.
No, it doesn't. It comes out to
Right, yes.
an extremely different
Yes,
answer.
that's
So
right.
then you times that by 1.96
Yes.
equals
Yeah. What do you get?
0.1856.
0.186.
56.
We'll say 0.186.
Go ahead.
Okay.
And then you add it and you subtract it from 8.2.
Yes. So
So
take
let's-
8.2 minus 1 point.
Oh.
8.2 minus 0.186.
Okay. Professor, can you scooch a little? 8.2 minus
That's what I had at first.
So you're getting it.
186 equals 8.014.
8.014.
14.
No,
Four?
see.
Alright, and what do you get for your high?
The decimal.
Your high would be
Interval.
8.2. 8.2 plus 0.186 equals 8.386.
Okay. Alright, and Francisco, that matches the back of the book, right?
Sure.
No, okay. Alright, that looks like what I got when I did this in class Monday and Tuesday night.
Yeah, that's right, yeah, that's right, yeah.
Okay, good, so can someone interpret that answer for us? As you give that interval to your boss, what do you say?
I am 95.5% confident that the standard deviation, am I wrong with terminology?
The average time,
The true
average time.
average time, yes.
True average time spent online.
Teenagers between the ages of 12 and whatever
Yes. Is
is
between,
between
8 hours.
8.014 hours and 8.386 hours.
Yes.
all is well. Alright. I am
Peace on earth.
it is 95, Lisa, not 95.5. I'm 95% confident that the true average time spent online for teenagers aged yada yada is between 8.041 hours and 8.386 hours.
Got it.
Alright. I think I wanted to do another example, if we're ready. I think we've invested some time in this, why not make sure we ingrain it? Let's do number 22.
All right. Let's just get this one. 22. Each one in there. The average salary for teachers and public schools.
Oh, yeah, that's it. It's gonna be. Let's see. You're gonna have to, you might wanna need to zoom in on it. So,
Students in the country.
We're done with that, 95% confidence. We said there's 2.5% chance. So we need to separate the upper 2.5% from the bottom 97.5. So we look for
200
0.975.
teachers.
Right? How did it work?
Okay.
yeah, there it is, okay. So
Salary.
that's 1.9.
65.83 salary. It's 6,800.
Sorry, excuse.
6,800, okay. When they use a terminology, average salary, how did you know that 60 was this? How do you know like each one of these?
Oh, because they said so they adopted, in a recent study.
Oh, average, and
Average
that's
salary.
that's the mean.
Yeah,
So that's what is, okay, got it.
yeah, and then they say in a recent study,
200 is the sample.
it was, the average study was based on 200, yeah,
Okay, got it.
exactly.
And now we just plug it in. Okay. Here we go, here we go. I like that one again.
How you feeling, Susie?
No, I feel all right, my computer is
Oh,
freaking out, so. I was doing.
Plus minus Z. Z. Now, is a Z always gonna be 1.96?
Depends on the confidence level. Why did we choose a 1.96 Z score?
It's his score.
Z, oh,
I don't
Z
know,
score.
that's what I'm confused.
Because it's 95%.
So we said, yeah, if we want a 95% confidence interval, we need a Z score of 1.96.
Yeah. It's the same thing, it's the same
What-
one.
Lisa, what if we wanted a 68.3%
No,
confidence
I'm
interval?
talking about the 99%.
We have a Z score of what?
So 99 is,
Help us out, Charlie.
68.3?
Yes.
1%.
I gotta go wait for my notes, sorry. Okay.
And what if we want a 95.5% confidence?
95.5, that's where I get 95.5 from.
Yes.
I heard that number.
Exactly, exactly.
0.5 and
It's gonna be
What's our
a lot.
Z in that case?
Was our Z in that case?
Yeah.
Oh, we don't have it that far. Right?
4.5?
2, because 95.5 is within, it captures 2%. 2%, 2 standard deviations captures 95.5% of the data. So those were just the easy ones. Like if we want a 68.3, Z score of 1, 95.5, Z score of 2. If we want anything else, we have to look on the table.
Okay.
I see what's happening, don't worry. It's like you kind of get it and then you forget because it's confusing. This happens whenever and every time everyone learns it. Do not be alarmed. It's like you're kind of like, you get pieces of it and then you lose it all of a sudden.
Alright. I'm gonna believe you. I'm gonna believe you, Professor Williams.
But let's do the 1.96. Right? If you want to be 95% confident, what are your chances of getting it wrong?
2 and 2 on the sides?
Yeah, that's right. But if you're 95% confident, you have a 5% chance of getting it wrong.
Right.
Okay. So in 5% chance, you could get it wrong high.
2.5 and 2.5.
2.5.
Of not being in the bell curve.
Yes, yes.
Okay.
So, alright, so you want 2.5, 2.5 here, 2.5 here. So you want to look on your Z-score on the positive side for the Z that separates the upper 2.5% from the bottom 97.5.
Okay. And how do you do that?
You look on the middle of the Z table for 0.975.
Isn't it 0.9938?
Okay, and that's where you get the 1.96.
Yes.
All right, sorry, it's just taking me a little longer, it's late, and it's just
No problem
complicated.
at all. Question, Charlie?
No, it's good.
It's 14.1.
Yeah, true.
That's the sample size.
All right. I hope during that interlude,
Oh, yeah.
everyone has calculated the answer. So what is our goal in this question?
Is to find out teacher's salary, how many people.
Yeah, teacher's salary.
The teacher's salary, what their average
Yeah.
mean in the country is.
Yeah, the average mean, the whole population.
Right.
All right, that's what our goal here. We want to find the average mean in the whole country. What do we do in our quest to determine that? We take a sample.
Oh,
And what do we come up with our sample mean?
our sample mean.
60,583.
Yes.
All right, that's just an estimate. We want to construct an interval where we're 95% confident. All right, and what is our z value going to be for 95% confidence?
1.96.
1.96. Excellent. So we are given the population standard deviation, 6,800. What is the standard deviation that we need, though? Somebody say it. What's this? I'll write it, you say it. What is this symbol?
Standard deviation of the sample mean.
Close. Can anyone give me a more precise wording on this?
Sample standard deviation of the sample mean.
It's the standard deviation. You can actually read it. Standard deviation of the sampling distribution of the sample mean.
Sample distribution of the sample mean.
Yep. Standard deviation sampling distribution is calculated with this population mean, 6,800, divided by the square root of the sample size, 200, which equals what? Lay it on me, Andy.
480.8.
480.8. Is that you, Lisa?
Yes.
Good job. All right.
And then you times that by the 1.96, right?
Actually, really, just leave it in your calculator. Don't round it until you get the final answer.
So then you times that by the 1.96, right?
Yes.
And you get 942.42.
Yes. All right, so plus or minus 1.96 times 480.8. What did you get for this, Lisa, when you multiply this together?
942.42.
942.42, okay? So you're gonna take 60,583 plus or minus 942.42. That's your confidence interval. And what's that
The
come
high
out to?
is 61,525. The low would be
59,640.
59,641 or whatever.
Okay. Yes. And what do we say to our boss when we present this interval? To her or him?
I'm 95% confident that the standard deviation of the average mean, go ahead, do it.
Yeah, okay.
No, you do it.
Go ahead, Francisco.
I was just gonna say I'm 95% confident that the true salary features around the country is between 59,741 and 60.
Okay, the only thing I would change about that, you're 95% confident that the true population mean
True population mean.
for average teacher salary,
For
teacher salary. So we're trying to determine the average teacher salary in the whole country. And you actually, Lisa, you started off with that question, that's what we're trying to confuse. But once you did all those calculations, you forgot, and that's understandable.
That's 2 hours and 20 minutes later. You got it.
All right, so what if we wanted a 99% confidence interval? What would change about this problem?
The Z-score.
The one
The z-score.
Yeah.
What would it be instead?
2.33.
2.33.
You have 3.33? 2.33? Alright, let's figure it out.
Let's figure it out. Yeah.
Let's figure it out. So we want a 99% confidence interval. So let me draw a Bell distribution.
Chances
If of we're
getting
99% confident, what's our chance of getting it wrong, Julio?
0.5 and 0.5.
Yeah, 1% chance of getting it wrong, as Julio pointed out. 0.5% chance here. 0.5% chance here. And we could say 0.5%, or we could also say 0.005. Does everyone understand those two are the same thing? Alright, 0.005. So we need this z, the one that separates the upper 0.5% from the bottom 99.5%. So if we're looking on the table that I gave you last time,
Yeah.
you would look for 0.995.
49 and 51, there's no 5.
How much are there?
I said there's no 0.995 there, it's between 49
Yeah,
and
there is.
51.
Okay, that's fine.
Until
That's fine. You can choose you can choose either one, or you can average the two. Whatever you prefer.
2.58.
just 2.5.
2.575.
995.
2.575, 2.58, those would all be fine. So that's your Z for 99% confidence. You need a wider confidence interval to only have a 1% chance of getting it wrong. Alright, how you feeling, Lisa?
How do you feeling?
Alright. So,
Do we have something?
okay, let's get back to the slides. I want to mention one thing, margin of error versus standard error. So when we're calculating our confidence interval,
Okay.
alright, ready to move on? Alright, when we're calculating our confidence interval, we do the sample mean plus or minus all this junk. Alright, it encompasses the z, and this is the standard deviation of the sampling distribution of the sample mean. You'll hear me say that several times throughout the quarter. This, everything put together, is what we call the margin of error. And I think actually Lisa calculated this for us. She said this z-score times the standard deviation of the sampling distribution of the sample mean. She said that's some amount that we plus or minus. And we'll call that the standard, or excuse me, we'll call that the margin of error. This, just this part here, the standard deviation of the sampling distribution of the sample mean, a lot of words, and I encourage you to use them, especially as you're getting used to it, and just trying to intuitively understand what that means, and I'll try to use it as frequently as possible. But if you get tired of saying all those words, you can instead say standard error. This will
Standard
become,
error instead of saying sampling distribution of the sample mean?
instead of saying the standard deviation of the sampling distribution of the sample mean.
Jinx.
Right.
This will become useful because we'll do other stuff like this. We'll do the standard deviation of the sampling distribution of the sample proportion difference. We'll do the standard deviation of the sampling distribution of the sample mean difference. We'll do some different things, and you can call them all standard error. Alright, so that's definition of margin of error. Okay. Last little section here. We're making some assumptions in this last problem that are not realistic in the real world. Remember, we were given the standard deviation of average teacher salary, or average standard deviation of teacher salary, being 6,800. We were just given that. Did you think that was a little weird? Somebody just gave us that?
Yeah, I really did.
No, it was a mess.
It was a little odd. How would we know
I
that?
had to pause.
Yeah, how would we know that if we don't know anything else about this? Alright, so the thing is, in the real world, we will not know that. So we will need to make a couple of adjustments. One, we'll need to calculate it ourselves. Do you remember when we talked about standard deviation? This was population standard deviation. Do you remember what this was?
Sample.
Sample standard deviation. Alright, and this was a little bit bigger. We did a, divided by n minus 1. It's fine if you don't remember that, but this sample standard deviation, we just made it a little bit bigger to account for the fact that we had less information. So when we make it a little bit bigger, this confidence interval is going to get a little wider. So for the same level of confidence, we can still look at our boss and say, I'm 95% confident of this, that it contains a true population mean. It just needs to be a little bit wider. So because of the unknown factors, we will calculate this ourselves, and we will make this a little bit wider. That's one thing we'll do. The second thing we'll do is we'll use a different distribution. We won't use the z distribution, we'll use something called the t distribution, which is also a little bit wider.
Okay.
Alright, so just make sure you intuitively understand the two things we're going to do. One, we're going to use sample standard deviation, which is a little bit bigger. And two, we're going to use a different distribution. So instead of 1.96, we're going to use like 2.03. And we're going to look on the table to determine exactly what it is, but it's just going to be a little bit bigger to account for the unknown factors. So the t distribution, this is the normal distribution we've been using where we get to 1.96. Now we're going to use the shorter, fatter t distribution, where instead of 1.96, it's going to be like 2.04 or something like that.
Okay.
It's just going to be bigger. How much bigger? Well, it depends on our sample size. The t-distribution is a family of distributions that has a different z-score, or t-score, excuse me, for each sample size. If you have a really small sample size, say 5, then you have a really short fat distribution. If you have a larger sample size, say 15, then you have a taller, skinnier distribution. What that means is for the smaller sample size, you need a wider confidence interval because you have less that you know. The bigger the sample size, the more precise you can make your confidence interval. The t-distribution uses something, instead of calling it sample size, they call it degrees of freedom. There's a mathematical definition for that. I don't want to go into it. I just want you to know that degrees of freedom is the sample size minus 1.
Okay.
Degrees of freedom, sample size minus 1.
Got it. So now it's got it.
And I think that's on the next page.
Yep.
N minus 1. N minus 1 represents independent terms. And this is called degrees of freedom.
We're coming to the end. Thank
Alright,
God.
so that's going to bring us back to something that should be very familiar. This formula, it should look familiar, right? It's just with a few little differences. Alright, we have the t here instead of the z. And we already know the t is just going to be a little bit wider to account for the unknown factors. And then we have the s here instead of the population standard deviation. And that's also going to be a little bit wider to account for unknown factors. But the process is exactly the same. Sample mean plus or minus some number of standard deviations, and this is our standard deviation of our sampling distribution on the sample mean. AKA standard error. Okay.
You go, girl. You got it.
Alright. So let's read the t distribution first. Let's do that. Let's go to our t distribution and let's read it. So flip in the back of your book. I'll pull it up here so if you don't have the book. If you have the book, just turn to the z distribution and turn over one page. this is T. Alright, can you see that? Yeah, you can see that, right? Okay, so the T distribution, we've got degrees of freedom here in the left-hand column. Degrees of freedom is sample size minus 1. And this is actually even a little bit easier to read than the T distribution, because we look on the right tail area in the top row, and the right tail area for a 95% confidence interval are, actually let's keep this one because I already have this up. So suppose we want a 99% confidence interval. Alright, how much area is going to be in the right tail?
0.05.
1/2 of 1%, and 1/2 of 1% in the left tail. So the T distribution just says you go straight to the right tail area, which is 0.005. That is 1/2 of 1%. And suppose you have a sample size of 8. What is your degrees of freedom?
7.
Yep, so 7 with right tail area, your T value would be 3.499. So you'd go plus or minus 3.499 standard deviations from your sample mean. Alright, suppose you want a 95% confidence interval. What is your area in the right tail?
2.25.
Yes, 0.025. Okay, and suppose you have a sample size of 13. What is your degrees of freedom? 12. Alright, so then for a 95% confidence interval, you would, your T value would be 2.179.
Oh, because you got a minus the 1. To go from 13 to 12, right?
Yeah, exactly. Exactly. Alright, now notice these, this is 95% confidence right here, this 0.025. What's happening to these numbers as we get a bigger and bigger sample size?
They're getting smaller.
Smaller. They're getting smaller. What do you think is going to be at the bottom of this chart? Okay, I'll kill the suspense. 1.96. So if we have a really large sample size, then we can use exactly the same thing we used on the Z distribution. Alright, let's do a sample, or let's do page 256, 7.7. Cancel that. Let's do, is that what it said? Yeah, 256, 7.7. Yeah, that's it, right? You can see that. Alright, so this is another social media example. Let's, instead of having a sample size of 50, we have a sample of 5, and we don't know the population standard deviation. Okay, so we've got these 5 teenagers who are spending time online. One spends 8, one spends 12, one spends 14, one spends 6, one spends 10. Alright, so you need to find the sample mean and the sample standard deviation, and then you need to show the 90% confidence interval for population mean of social media time. So, think about that for a minute while I erase this. Alright, so how do I calculate the sample mean?
You
Add them all together, divide by 5, okay? Then how do I calculate the sample standard deviation? Do you remember we did that with those 3 employees? One made 3 widgets, one made 5 widgets, one made 7 widgets?
You add the sample minus the, by the mean.
Yep. Check it out. Alright, so this is the mean, 10. Alright, and we take the average distance, the difference between 8 and 10 squared, 12 and 10 squared, 14 and 10 squared, 6 and 10 squared, 10 and 10 squared, and we divide by what? N minus 1, right? So it's a slightly smaller number we divide by, which makes it a little bit bigger. So the number is 3.6. Alright, and then here, let me hide this. So, show me the 90% confidence interval for overall campus population mean. So we've got some important information here. Our sample mean is 10 hours. Our sample standard deviation is 3.16. Alright. So let's calculate our standard deviation of the sampling distribution of the sample mean. How do we calculate that? Same way we calculated it last time, pretty much. Go ahead, Rebecca.
Standard deviation. 3.16.
Yes. Divided by?
Divided by the square root of 5.
Yep. Alright. So we'll crunch that. Actually, don't crunch it, I don't know what it is. Someone just go ahead and give us that answer.
2.36.
2.36?
Wait.
No,
I guess
1.1,
that's the square root of 5. Hold on. So,
2.6.
get out of the way. You make a better door than a window. I can't see. Yes, you.
I have 1.143. 413. Yeah.
What?
1.413.
Yeah, 1.413, got it. That's what it
Alright, perfect.
confirmed.
Alright, what is our t value then? For a 90% confidence? If there's a 90% confidence, what's the chance of getting it wrong in each tail?
5.
5%. So we look on the t table for 5% in the right tail. We go down for how many degrees of freedom?
4. No. Is it 4? 5 minus 1?
4 degrees of freedom. And I don't want to scroll back to it, but what do you got, Lisa? I mean, excuse me, Susie. Sorry. I know you're Lisa, you're Susie. So Susie is looking for 5% in the right tail, 4 degrees of freedom, and she's going to get what?
2.132.
Yes. Brilliant. Brilliant. So, we're going to take the sample mean, plus or minus, what Susie gave us for the t-score, times this, we know this to be 1.413, and it's going to come out between 6.99 hours and 13.01 hours.
Try later.
Make sense? Alright, now I feel like a bit of a torturer here, but I feel like it's in your best interest to do one more example.
No.
You'll thank me for it later. Yeah, do you want to do, let's do one more, let's do number 34. Actually, never mind, let's not do 34. Let's not do this one, I want to explain one thing to you about the t-distribution, which will take maybe 4 or 5 minutes, and then we'll go home.
Okay, cool.
Okay, so the thing about the sample we just used, or the example we just did, What was the sample size in this? 5, alright. And what did we say, how can we ensure that the sampling distribution of the sample mean will be a normal bell curve?
30.
Sample size of 30 or more. Okay, so it has to be sample size of 30 or more to ensure that the sampling distribution of the sample mean is normally distributed. Now there was an exception to that, and I said, well, this will come up at the end of the class. Does anyone remember what the exception was?
If you have like a really small group, right?
If the parent population is normally distributed. So remember we looked at 2 towns, one was normally distributed, one had skewed income levels. Alright, so for the one for skewed income levels, we definitely need a sample size of 30 or more to ensure that the sampling distribution of the sample mean is normal. But the one that was normally distributed, we're cool. We don't need a sample size of 30. We can have a sample size of less than 30. And you'll note, on this problem, it told you, it gave you this assumption. It said, assume the population distribution of times is normal. So it told you that you could assume that the standard deviation of the sampling distribution of the sample mean would be normally distributed because the whole population is normal, regardless of the sample size. So if you see this, you know it's okay to make these assumptions even if the sample size is less than 30. So you want to keep that in mind.
So if not, it's gonna be like sporadic or can't be measured?
Yeah, we can't make, yeah. We cannot assume, we need at least a sample size of 30. And I realize this sounds unnecessarily complicated at this point, but it's just, I need to just kind of get it into your head so that once this becomes clearer, we can distinguish these things.
Oh, makes sense.
Okay, alright, makes sense. Thanks. Sorry for making it sound complicated. It makes sense. The bottom line on this is because the population standard deviation was unknown, we needed to do our 2 adjustments. We needed to use the t distribution, and we needed to use the sample standard deviation, both of which are a little bit bigger. But the reason why we could even do anything to begin with is because we were able to assume that the population distribution is normal. And that allows us to make these assumptions of the sampling distribution of the sample mean. Alright, so I don't see any angry faces. So I feel like
I have a question.
I might have explained that semi-well. Yes, Lisa?
Off this, just back onto the syllabi. It says we have a quiz. Did we have a quiz? Was I supposed to take that quiz? I thought I was supposed to take it here. No?
No. You take the quiz on Blackboard. It's, try to get it done before coming to class. It's fine if you didn't take it. Just take it sometime this week. And ideally, you would want to take class 1 quiz and class 2 quiz before you come to class next week.
Okay, so for next week, make sure both quizzes are done for week 1 and 2.
That's ideal.
Okay.
It's
And the
okay.
homeworks are, you just submit them onto Blackboard.
Yes.
And if I'm late a week, it doesn't really, that's not a big deal, is it?
Yeah, so for the Excel homework, it's not a big deal if you're late on that.
But just make sure I do the quizzes every single week.
Try to do the quizzes, those are more important, but for these first couple weeks, if you need some extra time, take the extra time.
I have a question. If the homework's wrong, how would you be able to tell?
Good question.
Why is that funny?
No, but I did it, so I'm just like,
Did
there
you
were
grade
like
it?
2 of them, like I have like question marks.
Oh, okay.
So,
Well, okay. So I will tell you, I don't grade those too meticulously. It's
okay.
just like, if you look like you put in a good effort, then I give you 5 out of 5.
Do you want work shown on the homework, or is it
No.
okay?
There's
to
no
just-
way that I can.
Yeah, you can't show work. I guess I could open up your Excel sheet and I could do, there's a function where I could see the formulas that you wrote.
Okay.
I'm not gonna do that 30 times though. I'm just gonna say, it looks like you got it done, so I'm gonna give you a 5 out of 5.
Alright, so I'm gonna submit the quiz, I'm gonna do the quiz this week, and I'm gonna do the quiz for next week before I come. And then
If
try to
you-
get the homework. done.
Yes, if you can, but if you feel like you're gonna fail both quizzes, don't take them. Call me, email me, we'll try to get you up to
We
speed.
all heard that.
Because once you take the quizzes, I can't change your score. But if these first few weeks you need a little extra time before you take the quizzes, fine. We'll try to get you up to speed as quickly as possible, but if you feel like you have no idea on the material, then hold off on taking the quiz.
Okay, one more question.
Yes.
The holidays are coming up. Is each class consistent weeks, like 1 through 10? It's like I'm going the week of Christmas, I'm going the week of New Year's, all that? Or is there any bye week at all for the holidays?
Yeah, there is. You got a
What is
syllabus, right?
Yeah, I do,
Yeah.
it doesn't say it.
Yeah, it does. It says on the left-hand column, it says the day. And I think, what do we have? When is Christmas? Is it a Wednesday?
No,
I think it's Saturday.
It's like a rip-off.
14th to 21st. Oh, so we have the week of Christmas off.
Yeah.
Okay,
Perfect.
Yes.
okay, great. Thank you.
And I'll be here for a while. If we have any questions, I'll be happy to go over them. You all should be very proud of yourselves for the work you did tonight. It's a lot. And I know taking a little extra time in the beginning when we redid the sampling distribution, the sample mean, I definitely hope it helped, but that takes its toll. I know, because I know you all got a little more tired towards the end of this class than my Monday and Tuesday section where I didn't go back like that, just because you're here longer, so it takes its toll. So I want to say I'm proud of you, thank you, and let me know if you have any questions, and I'll see you next week.